These three expressions are polynomials. The symbol x is called a variable, and that's because we can replace the symbol x in each of the expressions above with a number, i.e. we can vary its value. And when we do so, we generate another number whose value depends on the value that we give to x. So, for example, if we let x have the value 1, then the expression 2x plus 3 becomes 2 times 1 plus 3, from which we can calculate 5. And similarly, 5x squared minus x minus 6 becomes 5 times 1 squared minus 1 minus 6, which evaluates to minus 2. And of course, a similar thing happens with the final cubic expression, and that eventually evaluates to minus 9. Now, this procedure allows us to choose a number and to associate that number with another number generated by a formula. In short, we are using a polynomial expression to create a function, and to talk about such functions properly, we need to talk about the sets which we use to define them. So here we have a picture of a function defined using two sets. The function is called p. The numbers 1, 2, 3, and 4 are contained in a set which we indicate by this boundary. Similarly, the numbers 5, 7, 9, and 11 are also contained in a set. The set on the left is called the domain, and I've given it the name A. The domain contains those numbers which we can substitute for x in our polynomial formula. The set on the right is called the range, and I've given it the name B. The range contains those numbers which are produced by the polynomial expression, in this case the expression 2x plus 3. And that formula produces those numbers when we replace x by one of the numbers in the domain. And so here we see how to give the complete definition of a function. We have the function's name, p, we have the name of the domain set, and we have the name of the range set, and we indicate that numbers in A are associated with numbers in B via this arrow, and we have the formula for the function. In this case, we say p of x equals 2x plus 3, and this indicates that x must be one of the numbers in the domain. We can read this notation as P has domain A and range B, or more briefly as P maps from A to B. And of course this notation P of x, which you will already be familiar with, specifies the rule by which we calculate a number in the range set B given a value in the domain set A. Here we can see two similar diagrams for functions which I've called f and g, whose formulae are respectively 5x squared minus x minus 6 and 4x cubed minus x squared plus 7x minus 19. Now, in these diagrams, I haven't described the sets C, D, E, and F in any detail, so we need to specify these sets properly. We can calculate the value of a polynomial function for any real number. In other words, x can be any number on the number line. So for polynomials, we choose the domain to be R. And so here we could contrast polynomials with the function x to the minus 1, for example, which is not defined for x equal to 0. So usually we would make the set C equal to R, and we would make the set E equal to R, i.e. the two domains would both be R, where R is the name given to the set of all real numbers. On the other hand, the range of a polynomial function is the set containing only those numbers that the formula produces as we set x to any number in the domain. And usually it is quite tricky to decide what that set will be. And so, since it isn't clear which numbers exactly this formula or this formula will spit out, we are going to put a question mark next to the set D and the set F. Since it is difficult to specify precisely which numbers should be in the range for a function, we specify a different set called the codomain. And the codomain is a set which contains the range, but which is at least potentially larger than the range. And very often we choose the codomain to be the set of all real numbers R. So often we specify a polynomial function in this form. We have the name f, we choose the domain to be R, i.e. we can put any real number into the formula, and we specify the codomain as R. And of course we have the formula for the function. And in this format, the R on the left is the domain set, and the R on the right is the codomain set. Since the distinction between the range and the codomain is likely to be as clear as mud at this point, we shall examine it in rather more detail. To do so, we'll look at the domain, codomain, and range of the polynomial function with the formula 5x squared minus x minus 6. Firstly, let's think which domain we shall have for this function. Usually, we want to be able to calculate the value of f of x for any real number whatsoever, and the formula is defined for any real number, so we choose the domain to be R. Note that we have a choice over which domain we use. Now for the codomain, it's not clear which numbers can be produced by the formula for f of x, but whatever is produced by that formula will certainly be real numbers. So we choose the codomain also to be R. And note that we're not claiming that every single number in R will be produced by the formula. We're merely claiming that any number that is produced by the formula 5x squared minus x minus 6 will certainly be in the set R. What about the range of the function? Well, we can't choose the range. It is determined by the numbers in the domain and by the formula for f of x. And once they are chosen, we have to figure out what the range will be. In other words, we have to answer the question, what numbers does the formula f of x equals 5x squared minus x minus 6 produce if x can be any real number? Now for this particular function, we can determine the range by rewriting f of x into what is called completed square form, which is shown here. I won't go through all of the details, but we can show that f of x is always going to produce numbers that are greater than or equal to minus 6.05. So for this function, the range, which is the set of numbers which can be produced by this formula 5x squared minus x minus 6, is the set specified here. Y is in R such that y is greater than or equal to minus 6.05, which can be specified like this in what is called interval notation for the real number line. So we can specify this function in two ways. We can say that we have a function f with domain R and codomain R, and formula f of x equals 5x squared minus x minus 6. Or we can specify it as the function f with domain R and range minus 6.05 up to infinity, with formula f of x equals 5x squared minus x minus 6. And you should be aware that the domain-codomain specification is giving us less precise information than the domain-range specification. The domain-range specification tells us that the numbers that will come out of the formula will definitely be in this set, whereas the domain-codomain specification only tells us that we can expect to see real numbers coming out of the formula. And here we see graphs of the two representations. On the left, the domain-codomain representation, on the right, the domain-range representation. In both cases, the domain is the whole of the x-axis. However, for the representation on the left, the codomain is the whole of the y-axis, shown here in green, whereas for the domain range specification on the right, the range is the subset of the y-axis, shown in red. And we see that the range, the subset of the y-axis in red, corresponds exactly to the portion of the y-axis that is occupied by the graph of the function. We usually specify the codomain of a function, as opposed to its range, when it is too difficult to figure out what the range of the function will be. In this particular case, it wasn't very difficult to determine that the range was going to be the set minus 6.05 up to infinity, but for some functions it can be very difficult indeed, and it is simply easier to specify the codomain as R or some other large set, rather than to do the work to determine the range. And here are a few points of which you should be aware. First of all, we can choose a domain for a function, and often the choice of domain depends on what we intend to use it for. So for example, if we choose the domain to be all real numbers R, then that might be because we want a smooth function that we can differentiate. On the other hand, we may want a function defined only on the integers, perhaps because we're interested in what are called sequences, and so we would choose the domain to be the set Z, the set containing the negative, positive, and 0 integers. But in both cases, we have the same formula. And for this second case, we can see a graphical representation of the function with domain of integers. The integers are marked in blue on the x-axis, and they are the only numbers which we are allowed to put into the formula. So we get a graph which is defined only at these points. The second point to be aware of is that if two functions have the same rule but different domains, then they are different functions. So the two functions defined here are in fact different functions, even though I've given them the same name. The next point is that if we specify a rule for a function, but we say nothing about its domain, such as here where we've specified the function f of x equals the square root of x, then we usually choose what is called the natural domain, which is the largest set of real numbers on which the function is defined. And we should bear in mind that we cannot take the square root of a negative number. And so the natural domain for the square root of x function is the set of positive and 0 real numbers, which is specified in interval notation like so. And the natural domain of any polynomial function is R, the set of all real numbers. And that's because to calculate the value of any polynomial, all we have to do is add, subtract, multiply, and divide. And we can always do those operations on any real number we choose. And the final point is that we often choose a domain to allow us to create an invertible function from a non-invertible function. We do this by choosing a smaller domain, and this is called creating a restriction of a function. And so if we consider the function with formula x squared and domain R, which is shown in the picture below, that function is not invertible. And that's because, for example, the number 4 could be produced by squaring positive 2, or alternatively, by squaring negative 2. On the other hand, if we create a function with the same rule x squared, but a different domain, the domain containing 0 and all positive numbers, then this function is invertible, and its inverse function is the function the square root of x. And that's because in this case, for example, if we look at 4, that can only have come by squaring the number positive 2. There are no negative numbers in the domain to consider. And finally, although I've introduced the concepts of range, domain, and codomain in the context of polynomial functions, they're applicable to functions of any kind whatsoever.